Hi, you guys. We're starting the second part of blood flow, second week. So we're calling it blood flow 2. And this section has a lot on blood pressure, and we'll be talking about that. So once blood is ejected from the heart, it exerts pressure. Of course, it's going to exert pressure against those vessel walls, correct? Also, we want to think of how there's a continuous decrease in that pressure as it flows. So when it first is going out the aorta, you have a pressure X, let's call it 120 millimeters of mercury if you look thinking of systolic. And then as it goes into the smaller arterioles and goes traveling along, it makes sense that there's going to be a decrease in that pressure because you need a gradient. A gradient is going from higher pressure to lower pressure. And if there were no gradient at all, blood wouldn't move. So it makes sense that it's going to do that, correct? But what we want to look at is by how much pressure does it decrease? And this is what always blows me away, you guys. Because let's look at this diagram. You have pressure measured here on this chart in millimeters of mercury. And here, what's happening in the left ventricle and the arteries and the little arterioles and the capillaries, and then it's going into the venules and finally back into the right atrium, correct? And if we measure what's happening in the left ventricle, so in the heart, you have this extreme change in pressure, correct? Because at times it's going to be full of blood and exerting a lot of pressure, and at other times it's going to be empty of blood and exerting very little pressure. So it makes sense that this curve would go shoot up to 120 and then go down very low. But let's now eject it from the heart and have it go over to the arteries here. So if we have it moving over to the arteries, in the arteries, you're going to have a systolic pressure, which is the higher of the two pressures because you're squeezing and then release, and then squeeze and release. So when you are in systole, that pressure makes sense. It's going to be the highest. And even though the pressure never drops to zero, there's going to be a slight drop in pressure as the heart is in diastole. And there's a slight drop. So that's usually you go have your pressure taken. You get a number like 120 over 80. This is the higher and the lower. So 120 over 80 here, let's say in the brachial artery. And it's going to go up and down, and we're going to move on now to the region here of the arterioles. As it moves through the arterioles, notice that this level is dropping, correct? And then it's going to drop again. So this pressure is getting lower. Diastolic pressure is also getting lower. And this is going to continue to drop to the point where it's very hard to see a systolic here up at the top and a diastolic on the bottom. And it's going to start evening out. So why don't we use this middle line as the mean arterial pressure, right? Think the mean and then follow this line along and see what that line does. So we're taking an average, we're taking a mean. So that mean is around in the 90s here, and it starts to drop. And 90 millimeters of mercury, it's dropping to 80, it's dropping to 60. I'm going to keep dropping, and this is what is so remarkable to me, that in the capillaries, your blood pressure is around 30. Mean, right? An average of 30. Did you ever imagine that? And then as it continues on to the venules, look at this. It goes below 20. I mean, you always say, oh, my blood pressure is 120 over 80. Well, you're talking about the brachial artery. What's happening here in the venules is below 20. And as it finally reaches here, the right atrium, in other words, when it's finally getting back into the right atrium, it's below 10. It's probably below 5 because this is 5 here. So it's below 5. Is that amazing? That's crazy. So that fluid pressure is changing due to friction, due to resistance of the actual vessel itself. And the pressure waves are absent in the capillaries here. We don't see that systolic and diastolic anymore. And then again, by the time it comes back, it's going to be at extremely low pressure. What is blood pressure determined by? Let's look at that. 1, your total blood volume. So that makes sense, right? We have about 5 liters of blood, but if we were to be more hydrated, we drink more water, we have a greater volume of blood, and that's going to be at a higher pressure. And also, I'm telling you that sodium intake increases blood volume. Yes, you know that. If you eat more salt, you get saltier. You feel thirstier, and you will drink more water. So your blood volume increases a little bit so that your blood pressure would go up. They actually tell individuals who have very low blood pressure and are going up to high altitude, for example, to eat a little bit more salt than usual, increase the volume and increase that pressure. 2, compliance and elastic recoil of the arteries is going to determine blood pressure. So if they has the elastic recoil in the large arteries that are able to elastically contract again, they're going to serve as a pump. Now, take away all that compliance. If also when blood pumps through it and they don't stretch at all, they don't stretch and they don't recoil. That's what compliance is, the stretch of it. So atherosclerosis is going to decrease that compliance and the elastic recoil, so you've kind of diminished this ability to help the heart pump. It's going to change the pressure. What else? The viscosity of blood. So the milkshake analogy, right? The thicker the blood, what happens with pressure if the viscosity increases? We talked about it in terms of flow before. The high viscosity increases pressure because it's thicker and you need more force to be able to move that fluid along. So it's going to increase the pressure. So dehydrated is going to increase your blood pressure. Peripheral vascular resistance. So this is like the atherosclerosis. You have decreased diameter if you have cholesterol sitting in, blocking the lumen of that vessel. It's going to have to pump harder in order to make blood go through that vessel. And cardiac output. So the greater the cardiac output, the greater the volume of blood being ejected out of your ventricle, the greater the pressure. So it works sort of both ways. If there's more blood coming into the heart, then all of a sudden you have to contract harder, and that cardiac output's going to be larger. So greater volume, greater output, greater cardiac output, greater pressure. They sort of go together. So let's look at what mean arterial pressure is. I talked about that when I showed you that previous graph. Mean arterial pressure is the driving pressure for flow, right? If you have a high mean arterial pressure, it's going to flow. There's going to be greater flow or less flow depending on that pressure. How do you calculate that? Before I show you the formula, I want to talk a little bit about that. If you needed to take a mean, the first thought that you probably would have is to take the systolic pressure and take the diastolic, add them together and divide by 2. Correct? That seems like it would be a mean of your highest pressure and of your lowest pressure. And that would not be entirely correct. And why not? Because the heart spends more time in diastole than it does in systole. So you have to take that into account, the amount of time that it's in each of those. If they were equal time, then we could just do a straight average, but we can't do that because it's ejecting for a shorter period of time than it's filling. So the formula is going to take that into account. So mean arterial pressure is equal to 2/3 of the diastolic, because it spends more time in diastole, plus 1/3 of the systolic. So if you had to calculate the mean arterial pressure of a patient with a diastolic pressure of 90, okay, this person has a blood pressure of 122/90. So I'm going to take the 90 and multiply that by 2 and divide by 3, and added to the systolic, I'm going to take a third of the systolic, so I'm going to divide 122 by 3. So by plugging those two values into the formula, you would get your answer. I'm not going to tell you what it is. Let's get another example. If I had to measure the perfusion to an organ, because that's really why we care about this. It's like how much blood is actually arriving at an organ or arriving at a system. So the mean arterial pressure, again, 2/3 times diastolic and 1/3 times systolic. That ends up being 90, here, let me do this, 90 times 2, 180, divided by 3, correct? I'm multiplying it. That gives you 60, plus 1/3 of 140, which is 46.6. We add these together, and you get a mean arterial pressure of 106.6. Now, if you had forgotten that this is how you do it, and you just took 140, added it to 90, and divided by 2, you would get a straight average, which is fictitiously higher, a little bit too high, because remember, it's spending more time in the diastole. So this correction is important when we think of an average pressure, mean arterial pressure, or MAP. Regulation of mean arterial pressure. Let's think of that. The main factors that are influencing this mean arterial pressure are, we said, blood volume, which is associated to cardiac output, how much is being ejected out of the heart. And after you eject, what is that peripheral resistance? So this is a nice diagram. Here's cardiac output. It's coming out of the left ventricle. I'm forcefully pumping this into an elastic artery here that is stretching, and then it's going to compress, and then it's going to shoot off into the rest of the system here, which is all your smaller arteries and arterioles. And those are going to have variable resistance. So the atherosclerosis individual maybe has cholesterol accumulating inside. And now this, shown by this little toolkit here, is showing that that resistance can be variable. So we say that the mean arterial pressure is directly related to the cardiac output times the resistance. And I hope that's clear. And there's our graph again. If we wanted to look at all the factors influencing the mean arterial pressure, this is a really nice graph from your book, a flow chart. We think of mean arterial pressure determined by, 1, we said, blood volume. That's good. Well, how does that change? So let's think of that a little bit more. Well, it's determined by your fluid intake and your fluid loss, how much you're drinking and how much you're losing. And how much you're losing, how do you lose it? Well, this is easy. You're drinking. And how you're losing it, just change the color of my pen here. It may be urination, so it's regulated by the kidneys, or it's passive, you're out exercising, and you're going to have sweating and any kind of passive water loss. Okay, what else is it determined by? The effectiveness of the heart as a pump, determined by your heart rate. How effective is this heart? Is it pumping correctly? Does it have the correct heart rate? Is this working? And every time it pumps, what is that stroke volume? So as it contracts, how much of that blood is it ejecting, right? And that's going to determine pressure. Resistance of the system to blood flow. So that's peripheral resistance, determined by the diameter of the arterioles. And then the relative distribution of blood between arterial and venous blood vessels, determined by the diameter of the veins. So do you remember this? We went over this previously, where we were talking about what percentage of the blood is in the heart at any one time, what percentage is in the muscles, what percentage is distributed through the body. And most of it is going to be in the veins, and what's the diameter of those veins. So it's a really nice way in a flow chart to look at what that mean arterial blood pressure is and what it's determined by. Just going back to my pen. There is a really nice video that I posted for you on MAP, on mean arterial pressure, for you to look at. We're going to stop right here, and the next lecture then we'll start on this particular slide. Thanks for listening. Bye.